Okay, so the rest of this chapter is sort of a hodgepodge of results. We have something about the continuity of the derivative. We have LHopitals Rule. We have Taylor's theorem, and we have something about differentiation of vector value functions. Okay, so I'm not going to pretend that there's any sort of like line to the rest of the story. It's just sort of a bag of results. Okay. So in the book, Rudin calls this next result the continuity of the derivative. Okay. And he doesn't mean that the derivative has to be continuous. Right? In fact, he gives an example immediately. He says, well, look, so a remark that if you look at the function f of x is x squared sine 1 over x for x not equal to 0, right? So you have this this function that looks like the sine function, right? Oops. But it's multiplied by x. Looks like the sine 1 over x, but it's multiplied by 1 over x squared. Right? You have this crazy looking thing like this. Right? Then this guy is actually differentiable, right? This is, and you let it be 0 if x is 0. Now this function is differentiable, but its derivative is discontinuous at 0. Okay, so it's possible to have a function whose derivative has a discontinuity. Okay. Now, however, any derivative is going to have the following intermediate value property. So if you have some function that is differentiable, suppose you have a function that's differentiable and assume that the derivative at one endpoint is less than the derivative at the other endpoint. Then what we're going to see is that for any intermediate value gamma, right, between f prime a and f prime b, there exists some point in AB where f prime attains that intermediate value. Okay? So you hit every intermediate value. Okay. So. Yeah, so it may be discontinuous, but it can't have a jump, right? If I have f prime, if I'm looking at f prime couldn't look like this, right? It couldn't look like this, right? Because there would be some lambda that's between the value of f prime here and the value of f prime here that's never attained. Okay, right? Or it could never look like this either. Right? Could not look like this either, right? Because again, I've got some values, but I don't attain this lambda between here and here. Okay, and so the corollary of this is that f prime has no simple discontinuities. Right? It has only discontinuities of the second kind. Okay, and this is basically the proof right here. Right? A simple discontinuity is when you have left and right limits. Right? You have left and right limits, but you have a discontinuity. Okay, having a discontinuity, these are basically the only possibilities in that case, right? your left and right limits exist and are not equal to each other, or your left and right limits are equal to each other and your function is has a different value there. But neither of those is possible because of the theorem. So no simple discontinuities. Okay, and so here's the proof of the theorem. Says, well, consider the function g of t, which we create as f of t minus lambda t. Okay, so we've got our lambda, right? So let lambda be in f prime a, f prime b, right? Lambda is the intermediary value, and let's create this function here, right? And we're hoping, right, it suffices to show that g prime is 0 somewhere. Okay, so the rough idea is this. So you say, well, look, well, if you look at g prime at a, right, you're going to get f prime at a minus lambda. Well, f prime is smaller than lambda, so this is going to be positive. Okay, lambda is bigger than f prime at a, so this is negative. Right. G prime at b is f prime at b minus lambda, which is positive. Okay. And now I don't want somebody to say, I hope nobody's going to say, so g prime must be 0 somewhere in between. Right? That would be wrong. Because that would be assuming that g prime is continuous, right? We're not saying that g prime is continuous, right? Okay, so we're not going to say that. Instead, we're going to say, so g prime cannot attain a minimum at A or B. Right? It doesn't attain its minimum at the endpoints.
How do you know that?
How do you know that? I'll let you think about it for 1 minute. No. I'll let you think about it for 1 minute in a minute. Okay. But right now, let me finish it up. Okay. So g prime can't attain its minimum at A or B. However, wait. G cannot, I'm sorry, G, what am I saying? I'm crazy. G cannot attain its minimum at A or B. Yeah, okay, now you're okay. Yeah. Okay. Now, g is continuous, right? Because it's a differentiable function minus a line, right? So, and it's on AB. So by the extreme value theorem, right, says that g attains a minimum in the interior, and so that's where g prime becomes 0.
on B because what?
Well, remember f is a differentiable function, and this is also a differentiable function, right? It's the function multiplied by negative lambda, right? So that's a line. So g is differentiable. It's a difference of differentiable functions. Okay, so is that clear? Yes, Adam?
Yeah, so are we talking about a global minimum here, or?
Yes.
I mean, okay.
Yes.
Okay, then that makes more sense.
Yeah, the extreme value theorem says that g is going to attain, its minimum.
Okay.
But I mean, attaining any minimum would do it because there the derivative would be 0. The extreme value theorem says that it'll attain its global minimum, but if we found any minimum, that would end the proof for us. Okay, is everybody okay with this thing here, that g prime a is negative, right? Right. So the slope, right? What is it saying at a, b? It's saying that if we look at the graph of g, the slope here is negative, right? And if we look at b, the slope here is positive, right? And so that tells you that you cannot have a minimum at a because you're basically like a line here, and you're basically like a line with a negative slope here, and here you're basically like a line with a positive slope. So now that needs to be made a little bit more rigorous. That's the intuition. To write it down rigorously takes just a little bit more energy.
So why do we need a lambda again?
Remember, we're trying to show that that f prime is lambda. Right? We're trying to remember what lambda is. Lambda is this value between f prime at a and f prime at b. Okay, so you've got your function. Your function has the property that the slope here is less than the slope at the end. Okay, right. The slope at the beginning is less than the slope at the end. Okay, and you're choosing a value between those two slopes, and we're saying that somewhere along the line here, we must have attained that intermediate value. Okay, and to do it, we say, okay, well, it'll a little bit easier to consider this function and see where its derivative is 0, right? Because where g prime, of course, is f prime minus lambda. So wherever this guy is 0, we're happy. Right? We're hoping that there's a place where this equals that. In other words, where g prime is 0. Okay, so we didn't really need to introduce this guy, but it's just a convenience. It makes it sort of cleaner to think about. E.
So the T point should be between A and B.
Mm-hmm. Yeah, because it's not going to be at A or B.
Okay, except right. A or B, but between them.
Mm-hmm.
Yeah.
Okay. Any questions? Any questions? Simple? Any questions? You look more cheerful than the last time I saw you. But you still don't look that cheerful. And I mean, I don't mean the exam. None of you look that good during the exam. I mean the last lecture. The page down then. You look a little better now. But
Have a lot of people dropped the class?
you think so?
Have they?
I don't know. I hope not. This is just post-exam, fallout, I think. Just after math exam. That was unintentional. Okay. Okay. Next thing, LHopitals Rule. LHopitals Rule. Okay. Those of you who know French know that this is how you spell hospital nowadays. In the book, it actually spells it like this. Oops. Oops. Which I always thought was wrong, right? Which I always thought was wrong, but in fact this is right. This is the old French way of spelling l'hôpital. It was, while l'hôpital was alive, this is how his name was written. It's only in later changes in French spelling that they changed the OS into an O with a circumflex on top of it.
They changed his name too?
Yeah. So this is actually the correct way, but I'm going to write it the wrong way. Okay, so you all know l'hôpitals rule. You might not have seen the proof of it, but you're all, I think, familiar with it. So say f and g are differentiable on some interval a, b, and a is less than b, and a could be negative infinity and b could be positive infinity. Okay. So you're differentiable on some interval, and it could be going all the way out to infinity, one or the other, infinity or both. And say that g prime of x is non-zero on that interval. So this AB, if you're thinking about it, really is probably going to be some small interval AB, okay, in which the denominator of the quotient that we're going to look at in l'hôpitals rule is non-zero. Okay, so and say that suppose that the limit of f prime over g prime as x goes to a on the right hand side is capital A, where capital A could be any number in the extended real values. Okay, so it can be A can be negative infinity or positive infinity or anything between. Okay, and you see why we needed g prime to be non-zero, right? Or why it's going to make sense, because this limit is going to be well, I guess anyway we need g prime to be non-zero. Okay, then if the limit of f of x and the limit of g of x as x approaches a is 0, then the limit of the quotient, right? If the bottom and the top both go to 0, then the quotient is going to go to the same value as the quotient of the derivatives. That's your old friend l'hôpitals rule. Right. Now Rudin throws in another possibility. He says, if this happens, or if you just have that the denominator goes to infinity. Then the limit of the quotient will go to the same as the quotient of the limit of the quotient of the derivatives. Okay, that's kind of interesting. He extends l'hôpitals rule a little bit more than beyond what you normally think. Okay. Okay, so does anyone happen to know how to prove this? Anyone take a look at the proof of l'hôpitals rule? It uses the generalized mean value theorem. As people are either looking away or down. So for simplicity, let me just assume, so for simplicity, I'm going to take A to be a finite number. It's not that much different to do it for a infinite, but it'll be sort of cleaner to do it this way. Okay, so right, we want to show that that this limit is a, right? We want to show that the limit of this thing is the limit of the original functions. The quotient of the original functions is a. Say okay. Well, so this is a limit argument, right? We want to find a neighborhood, a right-handed neighborhood of A, in which this thing is within epsilon of capital A, right? Right. That's what we want, right? We want to show there exists a delta such that in a plus delta, f of x over g of x minus a is smaller than epsilon. Right? That's what the limit being a from the right-hand side means. Right? That's just the definition. Okay. So we know we have that the limit of f prime over g prime is a, as x is a plus. So there exists a delta such that for any point c in a plus delta, f prime of c over g prime of c minus a is smaller than epsilon over 2. Right? We know that the limit of the quotients of the derivatives is a. We're trying to show that the limit of the quotient of the original functions is a. So we can make the limit of the quotients as close to a as we want. Right? And so we do. We make them within epsilon over 2.
Do you pick any epsilon? Epsilon over 10?
Yeah. If you want, you can just bigger numbers down here. In fact, any number bigger than 1 for the denominator will be okay. 1.1, if you want. Or a billion. 10 to the 10. I don't know. My advisor always used 10 to the 10 instead when he was doing analysis. Okay. Okay. So we have this sort of magic interval, right, in which the quotient of the derivatives is close to a. Okay. So now consider any interval x comma y that's contained in that magic interval, a plus delta. Right. So x is less than y, and bigger than a, and less than a plus delta. So we've got a magic interval, a plus delta, and we choose any x and y inside there. Okay. The generalized mean value theorem says there's going to exist some point c between x and y such that f of y minus f of x over g of y minus g of x equals f prime c over g prime c. Right? That's what the generalized mean value theorem says, right? That you remember it's written something like f of y minus f of x times g prime c equals g of y minus g of x times f prime c, right? But g prime, remember, g prime c is not zero, so we can divide by g prime c. Okay, and g of y is never equal to g of x, because if it were, then there would be some point in between where g prime is 0, but again, g prime is never 0. So we can divide by gy minus gx. Okay, and that starts to look suggestive, right? Starts to look like L'Hopital's rule is coming close. Okay. Is everyone okay with the generalized mean value thing? Any questions? Okay, so right, but we just said that we are in the magic interval where this number is close to a, right? So this number here, this thing equals this, but this thing lies between, no, I should say lies inside the epsilon over 2 neighborhood of a. Right? F prime over g prime is within epsilon over 2 of a, right? Or if you want, you can say is less than a plus epsilon over 2 and bigger than a minus epsilon over 2. The same thing. Okay, so now take the limit as x goes to a plus. Take the limit as x goes to a from the right-hand side, and use, suppose we're in this case, okay. F and g both go to 0, right? F of x and g of x go to 0, right? F of x and g of x, both of these guys go to 0, right? And so you end up with f of y over g of y. So right, so these guys, sorry, this thing lay between a minus epsilon over 2 and a plus epsilon over 2, right? And then you take a limit as x goes to a plus. Okay. What you get is that then f of y over g of y has to lie between a plus epsilon over 2 and a minus epsilon over 2, although possibly it could become equal to them. When you in the limit, it could actually in the limit it could actually become equal. Like just because if some function is you have some function and it's less than some number for all values of x, but in the limit as x goes to some point, it could actually become equal to it, right? I should put that on the side as an exercise, right? So exercise/fact. If f of x is smaller than a, say for all x, then the limit of f of x as x approaches some point is smaller than or equal to a. Right, you can sort of see how that might happen, right? You have some function, and it's always bigger than 0, but if you take the limit of it, you can actually get 0, right? Like 1 over x, as x goes to infinity. 1 over x is always positive, but as the limit of it is actually 0, right? So you attain, right? 1 over x is always bigger than 0, but the limit of 1 over x actually is 0 as x goes to infinity. Okay, so that's the fact that's why I need to put these equal signs here. Okay. Okay. So that's it, right? That gives us that. So what do we see? We see that thus, if y is in a plus delta, f of y, g of y minus a is smaller than or equal to epsilon over 2. Right? And so the limit, right? So the limit of f of y over g of y as x approaches a from the right-hand side is actually a.
Why did you have to do the epsilon over 2 in the first place?
Well, think about what you have to do. I mean, you don't really have to. If we didn't put the epsilon over 2 there, so suppose we just put epsilon here. Okay, suppose we just put epsilon here. Then what would happen? I would get less than or equal to epsilon here. Okay. But you know, in the when you're trying to prove a limit, you say, you know, given any epsilon, there's a delta such that these guys are within epsilon of each other. You don't say less than or equal to epsilon of each other, right? So the only reason I put in that epsilon over 2 is so that I could actually say, you know, less than epsilon at the end, rather than less than or equal to epsilon. But as you see, that's not at all crucial.
Okay.
Right? That's, I mean, the argument is,
Same.
If I can show this is less than or equal to epsilon, then, you know, I can certainly show that it's less than epsilon. I can just by taking a half along the way. So, you know, it's not a crucial point, but in terms of formality, you know, to prove the limit is this, you have to show that the limit, you know, given any epsilon, then these guys are within epsilon of each other, and this, if we didn't do that, we would get these guys are within less than or equal to epsilon of each other, which is not perfect, but the idea is already there. So yeah. Okay. Any questions? Right. So you see that this just is a consequence, a pretty immediate consequence of the generalized mean value theorem, right? That right. Right. You have right. You have f of y minus f of x by the generalized mean value theorem. You have something like this, right? Where here is x and here is y, right? And then you just you know, you just let x go to 0. That makes this thing vanish, right? And then you know, you let, you know, you can sort of think of it like this. This is not exactly rigorous, but it's, you know, it's close enough. Right? You got your a, you got your b. You use the generalized mean value theorem, and you say, well, I let x go to 0. Right? I let x go to 0. I'm sorry, I let x go to a from the right-hand side, right? And then I let y go to a, right? I let y go to a. And so when when the x goes to a, these guys vanish, right? And then when the y goes to a, I get the limit of the quotient of the original guys. And on this side, as y goes to a, this c, which is trapped between, also gets squashed to a, right? So I get, this is basically the same thing as the limit as c goes to a, right? And so L'Hopital's rule shows up in this way. Okay, so that's sort of the hand-waving argument. And to make it very proper, epsilons and deltas, you do it this way. Yeah.
For the conclusion there,
Yeah.
should it be y going to a?
Yes, I'm sorry. Yes, thank you. Okay. Okay. So I think I will not do the second version of L'Hopital's rule that Rudin includes, but I'll put it in the notes in case you want to look at it. Instead, let me go on to the next thing, Taylor's theorem. So approximation with so-called Taylor polynomials. Okay. So you have a function. And you know that its n-1th derivative is continuous on AB and is differentiable on the interior. These conditions should look sort of suggestive of theorems that we've seen in the past. You've got a function that's continuous on the closed interval and differentiable on the interior of that interval. Right? Mean value theorem is what this is hinting at and what we're going to use. So let this be a function and say the n-1th derivative is continuous on the closed interval and differentiable on the interior of that interval, and let alpha be some point in the closed interval AB. We define the n-1th Taylor polynomial of f centered at alpha as P of t is the sum of the kth derivative of alpha kth derivative of f evaluated at alpha over k factorial times t minus alpha to the k as k goes from 0 to n-1. Okay. So the Taylor approximation, the n-1th Taylor polynomial approximation of your function. Okay. I'm hoping that you've all seen this thing before in your previous math classes. But maybe you haven't seen the proof that we're about to show. Okay. So here's the theorem, right? So continuing the above notation. Right. So again, you've got this function. It's n times differentiable. Its n-1th derivative is continuous. given any point beta in AB, f of b is actually equal to p of b. F of beta is actually equal to p of beta, is actually the Taylor polynomial, but with some error. Okay, so, right, your function is actually basically the same thing as this polynomial, but there's this error. However, this error can be found as the nth derivative for some point x between alpha and beta, over n factorial times beta minus alpha to the n. Okay, so this gives you, right, this thing is the error. Right, this gives you a way of thinking about what that error is. For example, if you know something about the size of the nth derivative, then you know something about the size of the error. So an expression have an explicit expression for the error, and maybe can use to control its size.
What is the alpha in this case?
Alpha is this
Same
alpha
way.
is this point over here, around which you're expanding. You're taking your Taylor expansion. Yes, E.
How do we define the k?
K is your index. K is just an index from 0 to n minus 1.
Should we need to put a summation sign in that?
No. P of beta
Oh,
is this sum here,
right.
right? Evaluated at beta.
And there's still a remaining error
Mhm.
at the end here.
Yeah. So what this is saying is that your function, like how well is your function approximated by a polynomial? Okay, you've got some function, right? You've got some function. You take a Taylor expansion of it around some point alpha. Okay, so here's alpha, here's AB. You take the Taylor expansion of your function around some point alpha, right? That says that your function, your function is basically a polynomial. But your function isn't a polynomial, right? So how wrong is it? It turns out that this is how wrong it is. The error can be controlled as a function of the nth derivative.
So if you had the Taylor polynomial with k going from 0 to n, would that eliminate the error?
No, it would give you an error 1 degree higher.
Okay, so there's
Yeah.
always an error then?
Yeah. Yes.
So should that be equals or less, or well, no?
Equals.
I mean, yeah. So that error though. I mean, is that like exactly there?
Yes,
I mean,
yes.
It seems kind of.
Let me say it this way. Given any beta here, there exists an x between alpha and beta such that the difference is this.
Okay. Yeah.
Okay.
Yeah.
Maybe that's clearer. That's a bit more precisely stated. Okay, let's do it. We have only a couple minutes. Although the clock, I have to say, is like 2 minutes fast. So we've got a little bit more time than I think. Yeah. Okay, it's only 1 minute fast. No, 2. I'm not sure. Okay, so here's the proof. Let m denote the following constant: f of beta minus p of beta over betas minus alpha to the n. Right? In other words, the constant you get when you move this thing over to the left side and divide both sides by beta minus alpha to the n. Okay, so I'm just moving this thing to the left side, letting this thing be dividing both sides by beta minus alpha to the n. That thing is m, and of course we want to show that there exists an x where fn x over n factorial equals n. Okay, so I'm just rephrasing the problem. In other words, where fn x minus n factorial m is 0. So again, I've rewritten the problem, again, using elementary arithmetic. Okay. Okay. So now, consider the function g of t, which we let equal f of t minus p of t minus m t minus alpha to the n. Okay. And notice that if we take the nth derivative of that, then we get fnt minus n factorial m. So we're hoping to find a place where we want x such that g and x is 0. When we take the nth derivative of this thing has only n minus 1. It only goes up to n minus 1th power. So you take n derivatives of this polynomial, and then it vanishes. Okay. And when you take this thing, n times, you get n factorial. Right? Because at the end, you're going to get a 0 here, which will kill off this term. And each time you get, n minus 1, n minus 2, et cetera, et cetera. Okay. Okay. Okay, so we're hoping to find a place where this new function, where its nth derivative is 0. Okay, and if we do that, then we're done. So let's claim there's some point between A and B, between alpha and beta, where g and x equals 0. And the way we do it is by using the mean value theorem over and over and over. Okay. So you say, okay, well, look, observe that the kth derivative of A, kth derivative of P evaluated at alpha equals the kth derivative of F evaluated at alpha for k equals 0, 1, n minus 1. So just check that in case it's not clear. Thus, g alpha equals right, when you take the derivative of g and evaluate it at alpha, what do you get? Well, you're going to get f prime at alpha minus p prime at alpha. That's 0. And you get this thing evaluated at alpha is 0. Okay. And if you take higher derivatives, you're still going to get 0. Okay. So what happens is that all these derivatives, n minus 1, evaluated at alpha gives you 0.
What is f of alpha minus p of alpha equals 0?
Because of this observation here, that they have the same derivatives from 0 to n minus 1.
Why is that?
Let me finish. I'm sorry. Let me finish, and then I'll get to it. Okay. So okay. So now g of beta is 0. G of beta is 0. So by the mean value theorem, there exists some point between alpha and beta where g prime x1 is equal to 0. Okay, so look like this. Here's alpha, here's beta. G of alpha is 0 and g of beta is 0. So there's some point in between where g prime is 0. There's some point x1 where g prime is 0. Okay. But g prime of alpha is 0, right? If we look at g prime of alpha is 0 and g prime of x1 is 0, right? So there must be some point in between plot x2 where g double prime is 0, right? And then you just keep on going, right? There's going to be, you say, well, g double prime of alpha is 0, and g double prime of this x2 is 0. So there's a place where g triple prime is 0, and you keep on going, continue, and you use the mean value theorem, n times, and you get that there's a place where gn is equal to 0. Yeah, Adam.
I'm sorry, where did the g of beta equals 0 come from?
So look at what m is. M is f of beta minus p of beta over beta minus alpha to the n. Okay, right. So we're multiplying it by t minus alpha to the n. When we put in a beta, when we take g of beta, what do we get? We're going to get, this is going to cancel with this. We get f of beta minus p of beta, minus f of beta minus p of beta.
Okay,
So
thank
that's
you.
0. Okay, sorry to rush this at the end. If you want, I'll maybe talk a little bit more about it at the beginning next time, or you can just look at it. So I think the part that may not be clear is are these two lines here, but just work it out. It's actually just a calculation to see that these things are equal to, that these things are equal, and thus this is going to be equal to 0. Okay, that's it.